This is the 24th video in our series on topology, and our goal today is to find all of the homotopy classes of functions from S1 to S1. And by S1, I mean the unit circle thought of in R2, but it can really also be thought of as a topological space in its own right, as we have done previously. Now, I'd like to observe that this set right here is the set of all homotopy classes. And so we're going to say a class is, well, of this form bracket F using standard equivalence relation notation. So there we've got just the equivalence class of F as F goes through all continuous functions from S1 to S1. Now let's recall that that equivalence class will be defined as follows. It's going to be all functions G from S1 to S1 where G is homotopic to F. And I'd like to observe here that I'm not saying every time that we're dealing with continuous functions, but we are dealing with continuous functions. Now, let's recall that we say that F and G are homotopy equivalent if there exists a function F from S1 cross 0, 1 to S1, so that f of x comma 0 is equal to f of x, and then capital F of x comma 1 is g of x. Now in the previous video, we had arbitrary topological spaces here and here, but since we're restricting to this setup where we're going from S1 to S1, this is all we're going to worry about today. And now I'd like to note something, and that is via composition with this projection map, or maybe this gluing map that glues 0, 1 into the circle via this parametrization, cosine of 2 pi t and sine 2 pi t. A function from S1 to S1 can be matched with a function g from 0, 1 to S1, where g of 0 is equal to g of 1. We need those two to be equal because that's the gluing point, if you will. Okay, so anyway, let's look at this technical lemma. It's the so-called lifting lemma, which is going to help us along our way. So it says that if we've got a function that's continuous from 0, 1 to S1, like we talked about over here, and x is a real number where g of 0 is equal to cosine of 2 pi x sine of 2 pi x. We know that g of 0 has to be of that form because it's in the circle. Then there exists a unique function that's continuous, which we'll call g tilde. It goes from 0, 1 to r, so that for all t in 0, 1, g of t is cosine of 2 pi g tilde of t sine of 2 pi g tilde of t. So it's like we're taking that definition that g is giving us to the circle, and we're expanding it out to a function on the real line that perhaps takes into account that our function to the circle may not be 1 to 1. And so that would be extended into 2 points in the real line. Okay, so this is a bit technical, but we'll work through it. Okay, so we're going to start by setting u equal to the following. So it's going to be S1 minus this point 1, 0. And then we'll set v equal to S1 minus the point -1, 0. So those are like the east and west poles, if you will, that we're removing, I should say. Now we could draw pictures of these if we wanted to. So u would be like this circle right here. So maybe I'll put a u. And then v would be like this circle with the point removed right there. Okay, nice. And then just for the sake of notation, let's go ahead and set phi. I don't think this is standard notation, but we use phi here to go from R to S, be defined as, or S1 I should say, phi of t equals cosine of 2 pi t and sine of 2 pi t. So this is the function that like wraps the real line around the circle infinitely many times. It can be thought of as like some sort of extension of this pi over here, kind of obviously. And now observe that this rule right here is now equivalent to saying that g is equal to, let's see, what would it be? It would be phi composed with g tilde. So that's good to notice. All right, So now we can look at the pre-image of u and v under this map phi. So let's do that. So here I'll draw the pre-image of u, and here I'll draw the pre-image of v. Okay, so there we've got some number lines. So I've just labeled each of these ticks in the number line kind of above for the lower number line and below for the upper underline. And now let's see. Phi inverse of u, or the pre-image of u, has to contain everything that will quote-unquote miss 1, 0. But by the way that phi is defined, that's just going to be all integers. So the pre-image will be essentially like r minus z. So we could shade that like that. So I'm going to put an open circle around all of the integers, and then I would shade between. So I think that's pretty clearly the pre-image of u. Now, what about the pre-image of v? Well, here we are missing -1, 0. So we achieve -1, 0 when we end up with an odd integer times pi inside of this cosine thing. And so that means that, well, we're going to miss all of the half integers. So we'll miss like -3/2, -1/2, half, 3/2, and so on and so forth. But the pre-image will contain everything between. Okay, nice. So we've got something like that. And just to put it really into perspective, that means that when we map this with phi, we'll end up with exactly this set u here. That's the definition of the pre-image, huh? And then when we map the pink one with phi, we end up exactly with phi. Again, that's the definition of the pre-image. So we've got something like that. And then let's also note the following, and that is that the pre-image of u under G and the pre-image of v under G are going to be open sets in 0, 1. Well, that's because u and v are open sets in S1, and then G itself goes from 0, 1 to S1. But then we can write each of these as a union of basis open sets inside of 0, 1. So for instance, the pre-image of u equals the union over these open intervals AI, BI intersected with 0, 1. And then we can do the same thing for the pre-image of v. So we could write that as the union over, we'll say CI, DI intersected with 0, 1. Good, that's just using, again, basis open sets. Now let's also observe the following, and I think this is pretty clear, that the closed interval 0, 1 is equal to the pre-image of u union the pre-image of v. Well, that's because that's going to be the whole codomain if we union u and v together. So then if we take the pre-image of the whole codomain, we're going to clearly get the whole domain, which is essentially what's going on right here. Now, if we combine these two collections of open sets that we have forming the pre-image of u and the pre-image of v, we get an open cover of, well, 0, 1. But we know that 0, 1 is compact. So that means we can extract from these over here a finite subcover. So let's say that that's what we're doing right here. So take a finite subcover. And again, we're using compactness of the closed interval from 0, 1 in order to do that. Okay, so let's label the elements of that finite subcover, perhaps I1, I2, all the way up to IN. Then let's take this subcover and order it so that the number 0 is in I1 and the number 1 is in IN. And then I2 is between I1 and IN, and I3 is between I2 and IN, and so on and so forth. And then we can write down a form for all of these, kind of renaming our A's and B's as necessary. So we'll take I1 to be the closed 0 to the open B1 interval. And this is, of course, where B1 is bigger than 0. Again, we know that one of these is going to intersect exactly to something like this, which is open in the subspace topology. Okay, and then I2 will be equal to open A2 to open B2. And because we want these things to overlap, because we're covering all of 0, 1, we know that B1 is less than A2, which is less than B2. And now we just continue this process. So for example, I3 will be equal to A3, B3, both open. And here we have B2 is less than A3, which is less than B3. And then finally, if we continue this on and on and on, we know that IN will be equal to open interval AN to closed 1. Okay, so that's going to give us all of these numbers here. So we're going to have 0 is less than B1, which is less than A2, which is less than B2, which is less than A3, which is less than B3, so on and so forth, until we get way up here at the top. We've got Bn minus 1 is less than An, which is less than 1. And that's forming all of these intervals. Okay, so let's see what we can do with that. Okay, so here I've got this sequence of intervals that we just constructed. And now I'm going to lay out these intervals over and under, well, really they're on the interval from 0 to 1. I've just put some of them on top and some of them below, just to make it a little bit more visually easy to look at. Okay, and now we're going to introduce some new numbers, if you will. So let's set x0 equal to 0, and let's set xn equal to 1. So that means way down here, we've got our number x0, and then way up here, we have our number xn. And let's set x sub I equal to a sub I plus 1 plus b sub I over 2. So it's the average of those two. Notice that those are endpoints of consecutive intervals here. And this is going to be for all I between 1 and n minus 1. Okay, so let's see what that gives us. Well, that's going to be exactly the number right between ai plus 1 and bi, the midpoint, if you will. So the x sub 1 will be right between a2 and b1. So if we kind of triangulate that out, that's going to be this number right here. So I'll put my number x1 right there. And then my number x2 will be exactly between a3 and b2. So this perhaps right here would be my number x2. Okay, good. So now I've got this new sequence of numbers, x0, x1, x2. Observe that x3 will be somewhere over here, depending on the overlap, and then so on and so forth. And then, well, let's also note the following, that this closed interval from x0 to x1 is a subset of my I1. Remember, my I1 is, well, I won't write it down, but it's this interval from 0 to b1. I've already got it written down there. Okay, but now let's also note that if you take G and you apply it to I1, you'll either end up in U or you will end up in V. So I'll just write G of I1 is a subset of U or it's a subset of V. Now, without loss of generality, let's assume that it is a subset of U. Now, why? Because it's got to be a subset of one of them. We might as well take it to be U for the sake of argument. The argument is exactly the same as if it's a subset of V. And now what are we going to do? Well, now we're going to find an open interval in the pre-image of phi that contains x. Well, why does it need to contain x? Because x is this special number right here, which is g of 0. And that's what we're trying to define first for g tilde of 0. We're trying to define g tilde of 0. So immediately g tilde of 0 is x, and then we can extend that to a definition for all of g tilde. Okay, so let's get all of this written down. Okay, so like I said, we're finding an open interval in the preimage of U under phi containing x. And so let's recall what the preimage of U under phi looks like. It was this picture right here, essentially R minus Z. And now, how do we know that we can find one that contains x? Well, that's because, without loss of generality, we are assuming that g of I1 is contained inside of U, but that includes g of 0 right here. But recall that g of 0 corresponded to this point on the circle where the coordinate was built out of this x right here. So in particular, we've got this x, which might live right here. And now note, like I said over there, this interval that is part of the preimage of U under V is homeomorphic to U. So let's just look at this right here. So this would be that kind of sub-interval part of the preimage of U. And I think we can see that that is pretty clearly homeomorphic to all of U, because recall that all of U was this thing right here, this circle with the so-called east pole, for lack of a better word, removed. Okay, so we've got that set up. Okay, now we're ready to define the following. So now let's define G tilde as a function from I1 to R. Notice that in the end, we want G tilde to go from 0, 1 to R. We can't quite do that yet, but we can go from I1 to R. And it's going to be defined like this. G tilde is equal to the composition of H with G. But what's this function h, you might say? Well, it is the homeomorphism that takes this u up into this interval right here. So we're taking something from 0, 1. Well, in particular, we're taking something from I1, but that's going to be inside of 0, 1, kind of obviously. And then G is mapping it onto the circle. But the way that we've made our assumptions with this construction, it's mapped to this portion U in the circle. But then we apply this homeomorphism from U up to this piece of the subinterval inside of R to get this point up here on the real line. Okay, nice. So now by construction, we have our first thing that we need, that G tilde of 0 equals x. So G tilde of 0 equals x, as we need again. And then let's also note that we have G restricted to I1 is equal to phi composed with G tilde. And again, that's by construction here. Okay, so let's take a step back and see what we've done. Well, we've started defining our G tilde map, and we haven't gotten very far. We've just gotten to this small subinterval right here, this x0 to x1 subinterval. So now let's see where we can go from there. Okay, so to reiterate, so far we've constructed this G tilde from our interval x0 to x1 into R, where G tilde of 0 was x. And if you restrict G to I1, you get phi composed with G tilde. Okay, nice. But now the idea is to iterate this process. But every time we iterate this process, the roles of our choices from the first step are going to change. So let's see how that goes. So each time we'll pick the interval of either the preimage of U or the preimage of V containing G tilde of xk minus 1. And this is an iteration of the process because G tilde of x0, well, that's just G tilde of 0. That was equal to x. And our first choice in the first step through this was to pick the interval of the preimage of U or the preimage of V containing x. So if we do the same process, but each time pick the interval containing G tilde of xk xk minus 1, that allows us to define g tilde on a new interval. And that new interval is xk minus 1 up to xk. Again, each time using the homeomorphism between whatever interval we're on and the portion of u or the portion of v that we talked about before. Then essentially what we do is just glue all of those definitions of g tilde together so that we'll have g tilde defined from x0 to x1, from x1 to x2, from x2 to x3, and so on and so forth until we have a definition of g tilde on the whole interval from 0 to 1. And it's continuous because by construction, each of these components is continuous. And then by the way that we've made this choice right here, it'll be continuous at the switchover point as well. Okay, so now that we've shown that this g tilde can be constructed, let's show that it is in fact unique. Okay, so now we'll show that this g tilde that we've constructed before is in fact unique. So let's suppose that we've got another map, which we'll call maybe g hat, which goes from 0, 1 to r, satisfies the same conditions. And then of course what we want to show, if it satisfies the same conditions, is that it's exactly the same as g tilde. But well, what does that mean? Well, that means that if we do this composition of g tilde with phi, so phi composed with g tilde, that's going to be equal to g, just given our definition right here. Remember what our phi was, but that's going to be the same thing as phi composed with g hat, because g hat satisfies the same conditions. But then applying the definition of phi to all values of t between 0 and 1, we have the following. So for all t between 0 and 1, we'll have cosine of 2 pi g tilde of t, comma sine 2 pi g tilde of t equals cosine 2 pi g hat of t, and then sine 2 pi g hat of t. Okay, but that's pretty interesting. When will it occur that those two are exactly the same? Well, it in fact tells us the following. It tells us that g tilde and g hat always differ exactly by an integer. In other words, if we view g tilde minus g hat as a function, it takes in real numbers, but it only outputs integers. But it's a continuous function that takes in real numbers and only outputs integers. But it's a pretty easy result to show that that means that this must be a constant function. So in other words, g tilde of t equals g hat of t plus c, where c is some constant. Okay, but then what does that give us? Well, we know g tilde of 0 is equal to x, and we know g hat of 0 also is equal to x. So that means this constant must in fact be 0. But if that constant is 0, then these two functions are the same, and in fact we had uniqueness to start with. So now that we've done all of this work, let's look at a nice application of this lemma. Okay, so now we're going to look at an application of this lemma. So let's suppose we've got a continuous function from S1 to S1, and we've got the map pi from 0, 1 to S1 as defined over here. Okay, so now what we'll do is we'll set g equal to f composed with pi. And notice that that is going to give us a function from 0, 1 to S1 with g of 0 is equal to g of 1. We discussed how this would be helpful earlier. And now let's apply the lemma to g. Okay, so what that means is that our g evaluated at 0 is of the form cosine 2 pi g tilde evaluated at 0, and then sine of 2 pi g tilde evaluated at 0. So again, that's our function g0 by the lemma. There's that function g tilde that lifts g into this function on R. Okay, but then g of 0 is equal to g of 1 by our construction over there. So that's going to be the same thing as the cosine of 2 pi g tilde evaluated at 1 and sine 2 pi g tilde evaluated at 1 for the same kind of reason. But then by the same argument that we used just before for uniqueness, that means that g tilde of 1 minus g tilde of 0 is in fact equal to some integer. And this integer is in fact very important, as we'll see, maybe not in this video, but in an upcoming video. So we want to give this integer a certain name. So let's give it a name right here. So given a continuous function f from S1 to S1, let's define the winding number or degree of f by, we'll say f composed with pi tilde. So we're composing it with pi, and then we're doing this tilde action that lemma allowed us to do, evaluated at 1 minus f composed with pi tilde evaluated at 0. And so we'll call that, like I said, the degree of f. So I'll just set this equal to n, which is an integer, and then we'll use this notation degree of f for degree of f. But anytime we produce some sort of like technical definition like this, it's important to check out that this is a well-defined number attached to this function. But in fact, it's fairly easy to show that this is well-defined. The proof is essentially the same thing as the check of the uniqueness of g prime in the previous proof. So we won't worry about that right now. All right, so for example, let's consider this function f from S1 to S1, where f of cosine theta sine theta, recall that's an arbitrary element of S1, is equal to cosine n theta sine of n theta. So here we're just multiplying the angle by n. So for instance, this point 0 will obviously stay at this point 0. Here I'm writing theta equals 0. So that's how we're determining this point as the point 0. It's the angle. And then this point right here, which is pi over n, is going to get mapped to this point right here, pi. And then, for instance, and then this point right here, 2 pi over n, is going to get mapped all the way over here. Because notice if you multiply this by n, you'll get cosine of 2 pi, sine of 2 pi, which is the same thing as this over here. So here we'll have our 2 pi. And then I think you can see where this is going. Notice that this point right here, which is perhaps 4 pi over n, will get mapped over here to 4 pi. And then, well, this point at the very end, this 0, if you will, that's going to be the same thing as 2n pi over n. And that's going to get mapped way over here to this 2n pi. And so I'll put a dot, dot, dot for everything in between. So let's notice that we've taken the circle and we've essentially wound it around itself exactly n times. And I think that's how we can think about this as the winding number. Okay, so anyway, let's get to calculating the degree of f. It should be n based off of our observation that we've had right here. So let's note the following. And that is that f composed with pi tilde of t is pretty clearly equal to n times t. Just, I think the construction for that is pretty clear. But now let's look at f composed with pi tilde evaluated at 1 minus f composed with pi tilde evaluated at 0. Well, that's pretty clearly going to be n times 1 minus n times 0. In other words, it will be n. And so, well, what that means is that the degree of f in this case is equal to n, which again, since we described our function as winding the circle around itself n times, that gives motivation for the winding number again. Okay, so now we're going to look at another lemma, which we'll skip the proof of, and then prove a nice big theorem. So here we've got a lemma which can be thought of as like a homotopy lifting version of our previous lemma. So let's read through it, and like I said, we're going to skip the proof. So if f is a continuous function from 0, 1 cross 0, 1 into the circle, and x is a real number, so that cosine 2 pi x sine 2 pi x is f of 0, 0, then there exists a unique function, f tilde, which goes from 0, 1 cross 0, 1 to r, so that f is equal to cosine of 2 pi f tilde sine 2 pi f tilde, and f tilde of 0, 0 equals x. So again, this is essentially the same thing as we had before. It's just an extension to maybe instead of 0, 1 to S1, or really we wanted it to be from S1 to S1 with this identification down here. We'll see that this is like a lifting of functions from S1 cross 0, 1 to S1. In other words, a lifting of homotopies. Okay, so now let's prove a nice theorem. So here's the big result for the day. So let's suppose we've got continuous functions, we'll call them f and g, and they go from S1 to S1. Then we'll prove that f is homotopic to g if and only if the degree of f is equal to the degree of g. So this is a nice big result. Okay, so let's look at the forward direction first. So in other words, we'll suppose that f is homotopy equivalent to g, and let's say it is via a function which we'll call h. And h will go from S1 cross 0, 1, obviously into S1, where h of x comma 0 is equal to f, and h of x comma 1 is equal to g. Okay, nice. So what does that mean? So that means that if we take h and we compose it with pi, where the pi is like over here, and I guess we're composing the second variable of it with pi, but we won't be super careful about that, then that's going to be a map from 0, 1 cross 0, 1 into S1. Okay, nice. And now we can lift that to a map which we'll call h composed with pi tilde. And where is that going to go? So that's going to go from 0, 1 cross 0, 1 into r. And so again, that's using that previous lemma. Okay, and now let's observe the following calculation. And that is if we take h composed with pi tilde and we evaluate it at 1t, and we subtract h composed with pi tilde and we evaluate it at 0t, then this is continuous. And not only is it continuous, but it goes from 0, 1 in this variable right here, or this entry right here, into z. And that's via similar argument to what we had before. But then, again, if we're continuous and we go from 0, 1 into z, that means it's constant. But then we can use the fact that it's constant to calculate the degree of f and the degree of g as follows. So notice that the degree of f is going to be h composed with pi tilde of, let's see, 1, 0 minus h composed with pi tilde of, let's see, it'll be 0, 0. So that gives us, let's see, f tilde of 1 minus f tilde of 0 based off of our f over there. Okay. But then that's going to be the same thing via this being a constant function as of h composed with pi tilde of 1, 1 minus h composed with pi tilde of, let's see, 0, 1. But then that's going to be g tilde of 1 minus g tilde of 0, which is defined to be the degree of g. So there we have it. The degree of f is equal to the degree of g, assuming they're homotopic. Okay, so now let's do the reverse direction. Okay, so now for the reverse direction, we're assuming that the degree of f is equal to the degree of g. And then with composition of a rotation, we can just assume that f composed with pi of 0 is the same thing as g composed with pi of 0. So essentially we're giving them the same starting point, if you will. So now we lift each such that we have f composed with pi tilde of 0 is equal to g composed with pi tilde of 0. And from there, we can start the following calculation. So notice that f composed with pi tilde of 1 is equal to the degree of f plus f composed with pi tilde of 0, just by the definition of the degree of f. But now the degree of f is the same thing as the degree of g by our assumption. And then this number right here is the same thing as g composed with pi tilde evaluated at 0. But then putting these together, that's going to be the same thing as g composed with pi tilde of 1 by the definition of the degree of g. But that motivates us to define the following function, which we'll call h tilde, and it goes from 0, 1 cross 0, 1 into r. And it's going to be defined by the following formula. So h tilde of st is going to be equal to t, and then f composed with pi evaluated at s, and then plus 1 minus t, g composed with pi evaluated at. So when possible, this is a standard way of defining this kind of homotopy. But now let's note the following. And that is, if we take h tilde of 1 comma t and we subtract h tilde of 0 comma t, then kind of by definition, we'll get the degree of f, which is equal to the degree of g by our assumption. And then finally, let's set just plain old h of st equal to the cosine of 2 pi h tilde of st and the sine of 2 pi h tilde of st. And this is our final homotopy map. You can check pretty easily or pretty quickly that h evaluated at s0 will be our function f, and h evaluated at s1 will be our function g. Again, based off how those were lifted into this f composed with pi tilde and so on and so forth. Okay, so let's see the final punchline of everything we've done today, and then I'll leave you with some exercises. Okay, so the big takeaway is that the homotopy classes of continuous functions from S1 to S1 are completely determined by the degree. That's what we proved in the previous theorem. And then in the example right before that, we showed that for every integer n, there is a continuous function f from S1 to S1 that achieves a degree of n. But that sets up a natural bijection from the equivalence classes of the functions from S1 to S1 under homotopy equivalence to the integers, where we take this equivalence class of f to the degree of f. Now, here are some problems. So the first is to find all homotopy equivalence classes of maps from open01 to open01. And then the second one is if f and g are continuous functions from S1 to S1, where the degree of f is m and the degree of g is n, let's try to determine what the degree of f composed with g is. And that's a good place to stop.